If you were given these two velocity equations, would you be able to find the instantaneous acceleration at time equals 2 seconds? If not, I'll show you how. So we can start by asking ourselves, what is the equation for instantaneous acceleration in 3D? Now, if we remember, in 1D, the instantaneous acceleration equation is just a equals dv over dt. We can change it into 3D by changing the velocity into the velocity vector, which has x, y, and z components, as well as we could change the acceleration in 1D to the 3D acceleration vector, which also has 3 components in the x, y, and z direction. If we plug this in 3D, we get this equation here, and then we can plug the velocity vector in, and then we can distribute the dt and get this form here, which is the most useful form. And I just want to note, looking at this acceleration equation, we can break it down into components. Acceleration in the x is the change in velocity in the x direction over change in time, and then that's the same for the acceleration in the y and the acceleration in the z. And then another note about the 3D acceleration is the magnitude for the acceleration vector can be found using the Pythagorean theorem in 3D. We have this equation down below. This is how we find the magnitude of the acceleration vector in 3D, where the a in the square brackets is just the magnitude of the a vector, and then these ax, ay, and az are just the magnitudes in each direction. So now that we know everything we need to know, we can now apply back to our example. We can start with the acceleration equation that we found, plug in our values, vx, vy, and vz is equal to 0. We just plug in 0 in that direction, and if we do that, we get this expression here. And now we can compute these derivatives. So the derivative of just t, you could just bring down 1, and then t goes away, so it's just 0.2 meters per second. And then the derivative of a constant, 0, and then a derivative to the power 2, you just bring it down 2 minus 1, and then we get 2.4 meters per second cubed t for the second term there. So we can plug both these in, and we get this here. This represents the acceleration as a function of time. We got to plug in 2 seconds to find the instantaneous acceleration at 2 seconds. If we plug that in, we get this here, and then we can do the multiplication of the term on the right. Multiply the amplitudes, we get 4.8, and if we multiply units, we get meters per second squared. This will leave us with the equation below, just knowing that this is now the equation for the instantaneous acceleration at time equals 2 seconds. But we're not done here. We need the magnitude of the instantaneous acceleration, so we need to use the equation below here. So we can plug in the values we got in the equation for ax and ay. Assume az is equal to 0. Plug those in, and we get this here. Simple calculations, and we get this for the final answer, noting that this is the instantaneous acceleration in 3D at 2 seconds.